Bismillahirrahmanirrahim. This is Dr. Muhammad Jameel, and this is the next chapter, the elliptic integral. Remember, there are three type of elliptic integral. The first one is called elliptic integral of first kind. You see here, this is the incomplete elliptic integral of first kind, and this is incomplete elliptic integral of second kind, and this is elliptic integral of third kind. Question is that what is the purpose of elliptic integral? So remember, in sciences and technology we want thing in order we want thing to be short. So in order to write this very complicated expression in short form, we denote it by incomplete elliptic integral of first kind, that is f of k phi. Likewise, you know that sin x is actually sin x is equal to this infinite series. So actually sin x is short form of this infinite series. Similarly, cos x is very short form of infinite series of this form. Similarly, you know that this is gamma integral. So gamma integral is actually equal to this integral. So this integral or such type of integral can always be written in the form of gamma integral. Similarly, beta integral, you know that equal to this integral. So in order to show the form of this integral, we denote it by first kind or second kind or third kind. Let us define these elliptic integral. The incomplete elliptic integral of first kind is denoted by f of k phi, and it is defined at integral 0 to phi d theta over square root 1 minus k square sin square theta. Remember that the range of k is always between 0 to 1, in which phi is called amplitude of f of k phi or u, and written phi is equal to a amplitude of u, and k is the modulus, written as k is equal to modulus of u. The integral is also called Legendre form of the elliptic integral of the first kind. So you see here, we denote elliptic integral of first kind by f of k phi. And what is k? K is actually k square, and you note here k square is actually coefficient of sine square theta. So instead of k square we write here k. And what is phi? Phi is the upper limit of this integral. Phi is the upper limit of this integral. So elliptic integral of first kind we denoted by f of k phi. And remember that k between 0 to 1, if k is outside this range, then the integral of such type never be elliptic integral of first kind, even though those integral are in this form, but never be equal to elliptic integral of first kind, because k must be between 0 to 1. Similarly, if phi is equal to pi by 2, if phi is equal to pi by 2, then incomplete elliptic integral of first kind is called complete elliptic integral of first kind. And in that case, when phi is equal to pi by 2 and it is complete, it is denoted by kappa of k. Kappa of k, or simply k, or simply f of k और kappa of k, इस तरह से हम इसको भी डिनोट कर सकते हैं. So whenever elliptic integral of first kind is complete, then we denote it by f of k, kappa of k, or simply k that you see here. Similarly, elliptic integral of second kind is defined as, just write this expression, this square root expression, 1 minus k square sin square square root in numerator. So if we write this expression in numerator, then the resulting integral is called elliptic integral of second kind, and elliptic integral of second kind is denoted by e k phi. And k is the same, k comes from this k square, and k square is coefficient of sine square. Similarly, phi is upper limit of the integral, and k must be between 0 to 1. And if phi is equal to pi by 2, then this incomplete elliptic integral of second kind is called complete elliptic integral, and it is denoted by e of k. When elliptic integral of second kind is complete, it is denoted by e of k, or simply e. Similarly, remember, there is no other sign for complete elliptic integral of second kind. But for a complete elliptic integral of first kind, we have two sign. Number one, k of k or kappa of k, or simply f of k or f. Now, this is incomplete elliptic integral of third kind, and what we have done here, just you see this expression that you see from cursor. This is elliptic integral of first kind. So if we multiply elliptic integral of first kind by 1 over 1 plus n sine square theta, we multiply the root expression by 1 over 1 plus n sine square, then the uh, first elliptic integral became third elliptic integral, and the third elliptic integral is denoted by phi k n pi k n phi, and k and phi is remain the same, but what is n? N is the coefficient of sine square in this vector. N is the coefficient of sine square. Similarly, if elliptic integral of third kind is complete when phi is equal to pi by 2, then it is denoted by pi or pi k, something like this. So these are three type of elliptic integral. So in this whole chapter, remember that our aim is to return a given elliptic integral, uh, is to given a integral into elliptic integral. So before going to these example, first I give here some fast example of where our aim is to convert the given integral into elliptic integral. First of all, we recognize these integral whether they are first kind or second kind or third kind, and we have to determine what is k, what is phi, or whether they are complete or incomplete. So let's see first. Can you see here, this is elliptic integral of first kind. Why first kind? Because this root expression is in denominator, because root expression is denominator. And what is k square? K square is 3 by 2. K square is 3 by 2. So because this is first elliptic integral, we denote it by f, and k is square root 3 by 2. And what is angle? Angle is pi by 4, and it is not complete because angle is pi by 4. Similarly, see this second example. This is complete elliptic integral of first kind. Why first kind? Because this root expression is in denominator. And what is k? K is square root half. And what is angle? Angle is pi by 2, and because this is pi by 2 angle, so this is complete elliptic integral of second kind. We denote it by f of square root half comma pi by 2, and because it is complete, so no need to write pi by 2, so we just write f of k, and k is square root half. And you know that first elliptic integral of first kind can also be denoted as kappa of k. So this is complete elliptic integral of first kind. Now let's see third one. This is again complete elliptic integral of first kind. What is k? K is 2 by 3, and what is angle? Pi by 2. So we denoted f of 2 by 3 comma pi by 2, and we pi by 2 is not necessary to write here, so we write f of 2 by 3 or kappa of 2 by 3. You see here kappa of 2 by 3. Similarly, number 4 you see here, and because this root expression is in now in numerator, so this is elliptic integral of second kind. And what is k? K is half. And what is angle? Pi by 6. So we denote it by e of half comma pi by 6. And this is incomplete. Why this is incomplete? Because the angle is pi by 6. The next one is again complete elliptic integral of second kind. And why second kind? Because the root expression is in numerator. And what is k? K is square root half. K is square root half. And what is angle? Angle is pi by 2. So this is complete, and not necessary to write pi by 2 here, so we just write e of k. K is square root half. Similarly, you see number 6. This is again complete elliptic integral of second kind. And what is k? K is e. And what is angle? Angle is pi by 2. And because this is complete, so not necessary we write pi by 2 here, so we just write e of e. So you see this expression is e of e. Number 7 you see here is very different from first kind and second kind. Definitely it is elliptic integral of third kind. And what is k? K is, you see here, k square is 4 by 9, so k is 2 over 9, k is 2 over 9. And what is n? N is the coefficient of sine square in this vector, so n is 1 by 4. I write 1 by 4. And what is angle? Pi by 3, pi by 3. And this is incomplete elliptic integral of third kind. Next, you see number 8 is the elliptic integral, again elliptic integral of third kind. And this is what is k? K is square root 2 over 3. And what is n? N in this time is minus 1 by 4. Note that n in this time is minus 1 by 4. And what is angle? Angle is pi by 2. And this is complete elliptic integral of third kind. And definitely you can denote it by without pi by 2, because this is complete and not necessary to write angle pi by 2. So just you can denote it by pi square root 2 over 3 minus 1 by 4. Next you see here is the example. In this example, if we have given if k is between 0 to 1, then we have to prove this expression. This expression is equal to this series. So first of all, you see here this expression is actually elliptic integral of first type and complete. Why first type? Because this expression is denominator. And why complete? Because angle is pi by 2. And first complete elliptic integral of first kind is also denoted by kappa of k. So actually we have to prove that kappa of k is equal to this infinite series. So let's prove this result by knowing the negative binomial theorem. We know that you can find this formula in any handbook of mathematics for negative power. The binomial formula of negative power is 1 minus x power minus half is equal to this series that you see here. And this series can also be written in this form. On the left hand side can be written in this form as 1 over square root 1 minus x is equal to, and then 1 I write as 1, and then you see this second term, minus minus is plus, and half and x. Similarly, this third term, this third term you can check, you can is equivalent to 1324 x square. Similarly, this fourth term is equal to 135246 x3. Similarly, you can make the next term. What will be the next term? 1357 and what is denominator? 2468 and so on. So the above binomial formula can be written in this form. Actually what we want to make this complete expression. We actually want to make ये complete expression हम बनाना चाहते हैं. तो इसके लिए अब हम देखते हैं कि इन दोनों में क्या फ़र्क है. What we see here, so instead of x we have here k square sin square theta. So first we put x is equal to k square sin square theta in this for binomial formula. So I put x is equal to k square sin square theta, and you see this series. And then in order to make complete expression, this we integrate on both sides from 0 to pi by 2 d theta. So I integrate and we get this expression. Now in this expression you see here there are some unknown expression that we have to determine. What is the first one? This is the first integral that we have to determine. This is the second interval, and what is this is the second integral, and what is this? This is 0 se pi by 2 sin square d theta. This is third one, and what is this? This is 0 se pi by 2 sin 4 theta. And this is the fourth one, and what is this? This is 0 se pi by 2 sin 6 theta. In order to determine these sine integral, you know that from NED first year, the very famous reduction formulas of sine, cosine, etc. You see here we need here sine formula. So this is the sine formula of 0 to pi by 2 sine nx dx. And what is this formula? This formula we can break into two parts when n is odd and n is even. Remember, when n is odd or n is even, the expression is same, but the difference is that when n is odd, this expression n always by 2 by 3, and when is even, then this expression is always end by half. But in even case, remember, we have to multiply this expression by pi by 2. So whatever your n is odd or even, your this expression is same. Remember, your expression this expression is same, but if n is odd, then this expression is end with 2 by 3, and when n is even, then this expression is end by half. But n in is even case, this expression must be multiplied by pi by 2. So let first see this expression. What is this expression? This is in numerator n minus 1, n minus 3, n minus 5, and so on. And what is denominator? N, n minus 2, n minus 4, and so on. The question is that how we stop this sequence. The answer is that whenever whenever you have either in numerator or denominator, whenever you get 0 or negative answer, then stop before that expression. So whenever you get in these expressions 0 or negative, then stop before 0 or negative factor. So whenever you get 0 or negative, stop before 0 and negative, and we get the answer. So let first calculate this very simple integral. Very simple integral, you see here, we get the answer is theta, and then put the limit 0 to pi by 2, we get pi by 2. And now see this second integral, 0 to pi by 2 sine square d theta. Here n is 2, so n is 2 mean we have in even case, and we have to put n is equal to 2. So I put n is equal to 2. What we get? 2 minus 1 is 1, so I write here, you see here 1, and then 2 minus 3 mean minus 1, and because this is negative, so I stop before this factor, that is at 1 I stop here 1, and then I put n is equal to 2 in denominator. So what we get? 2, I write here 2, and then 2 minus 2 is 0, so we get 0 here, so I stop before this factor, so we get only 2. And because n is even, so I multiply by pi by 2, I multiply by pi by 2, and you see here we get this factor only, and this factor is half, because n is equal to 2. So remember, whenever you have n is even, your last factor is half. So last factor half mean that you stop the sequence. If you don't want to remember negative or 0 case, you just remember whenever you get half, you stop. So because we get half, so I multiply pi by 2 and stop. Similarly, when in third term, you see here 0 to pi by 2 sine 4 theta. Now our n is 4, so now I just put n is equal to 4 in this expression. What we get? 4 minus 1, 3. So I write, you see here 3. Then I put 4 minus 3 mean 1, so I write 1, and 4 minus 5 mean minus 1, so I stop before this factor, means at 1 I stop. Similarly, in denominator I put 4, I write 4. 4 minus 2 mean 2, so I write 2, and 4 minus 4 0 means we have to stop before this, so I stop 2, and then because you see here in last here is 1 by 2, so this means n, our n is even, so I multiply pi by 2, and this expression we can also be write as 1324 into pi by 2. Now you see here we obtain from this reduction formula these two terms, and now what is the symmetry in these two terms? You see, this is 1 2 pi by 2, this is 1 3 2 4 pi by 2. So if without using for above reduction formula, we can write the expression 0 to pi by 2 sine 6 theta d theta same like this here. How? 5 3 1 how 1 you see here 1 3, so here we have 1 3 5, and in denominator 2 4 6 into pi by 2. Similarly, if we have 0 to pi by 2 sine 8 d theta, so what we get? We get 1 3 5 7, and in denominator 2 4 6 8 into pi by 2. Now put all these values values of integration into this series, we get this formula, and in all these terms you see here pi by 2 is common, so I write pi by 2 is common, and what we get from second equation, you see this is half, so we get half square and k square, and you see here in third term 1 3 2 4 1 3 2 4, so we get 1 3 2 4 square k4, and similarly in the next term And so this is the complete elliptic integral of first kind is equal to this series that we have proved. So you see here, only this is the first example that is different. Now in all example, our aim in the next example to write the given integral into elliptic integral form. So let's see example number 2. In example number 2, we have to evaluate this integral into elliptic integral, and then at the end we can write into 3 decimal places. Remember this example 1, this example number 1 says that the first kind of elliptic integral kappa of k is equal to this series. So whenever, remember, if k is 0, then kappa of 0 can be written as pi by 2 1 plus half square, and here k, instead of k we have to put 0 square. Similarly 0 power 4, 0 power 6, and so on. Similarly, if we have kappa of 1, then you have to put, instead of k you have to put 1. Jazakallahu khairan.
This is next example, and in this example our aim is to reduce this elliptic integral into elliptic integral, whether elliptic integral of first kind, second kind, or third kind, and then we have to return in 3 decimal places. So now whenever you have only sine x or cosine, whenever you have only sine x, then our first aim is to convert into cosine x. So first let we convert into cosine x, and then we see what we have to done. So in order to convert this sine x into cosine x, we bring this transformation x is equals to pi by 2 minus y. Remember, whenever you have to convert sine x into cos x or cos x into sine x, we always bring this transformation x is equal to pi by 2 minus y. Such type of transformation you know from inter, convert the sine x or into cosine x, or cosine x into sine x. So x is equal to pi by 2 minus y, then this means dx is equal to minus dy. Similarly, when you have x is equal to 0, we have y is equal to pi by 2, and when x is equal to pi by 2, we have y is equal to 0. And remember, sine pi by 2 minus y is equal to cos y. So put this transformation into the given integral, we get this expression. We get limit pi by 2 0, instead of dx we have minus dy, and instead of sine x we get sine pi by 2 minus y, and sine pi by 2 minus y is equal to cos y. And I change the upper and lower limit. Remember, whenever you change the lower or upper limit of definite integral, then there should be minus sign. So that minus sign and this minus sign is plus. So minus minus is plus, and we get finally this expression. And now whenever we have this integral, remember, whenever you have only cosine y, our next step is to bring this transformation cos y is equal to cos square u. So remember, whenever you have only sine x, first convert it into cosine x, and then when you have sine x, then always when you have cosine x, then always bring cos square u transformation. So because we have cosine y, so I write here cosine y is equal to cos square u. Actually why cos square u? So that cos square u is equal to 1 minus sine square, because in elliptic integral, in all elliptic integral, we have 1 minus sine square. You see here 1 minus k square sine square theta, 1 minus k square sine square theta, 1 minus k square sine square theta. That's why we want that this cos y can be written in the form of cos square. So let cos y is equal to cos square u, and this give minus sine y dy is equal to minus 2 cos u sine u du. And from this expression we can write dy as 2 cos u sine u over sine y du. And this sine y can be written as square root sine square y, and sine square y can be written as 1 minus cos square u. And because cos y is equal to cos square u, so when I put cos y is equal to cos square u, we get 1 minus cos 4u. and cos for u can be written as 1 minus cos square u, 1 plus cos square u. So and we break this square root, so we get this expression square root 1 minus cos square u is square root 1 plus cos square u. But 1 minus cos square u, 1 minus cos square u is sine u, so this sine u and this sine u is cancelled. We get 2 cos u over square root 1 plus cos square u du. So this is the expression of dy. Similarly, if we have y is equal to 0, you see here the lower and upper limit of y is 0 to pi by 2. So we have, when y is equal to 0, I put y is equal to 0, and cos 0 is 1. So cos square u is equal to 1, and cos square u is equal to 1 mean u is equal to 0. Similarly, y is equal to pi by 2. From this expression we get cos pi by 2. Cos pi by 2 is 0, and cos square u, and cos square u is equal to 0 when u is equal to pi by 2. So put these transformation into this expression, we get this expression. You see here we have above this and this expression, they are same, and now we are putting these transformation into this expression. So our limit is the same, 0 to pi by 2, and 1 over instead of cos phi I write cos square u, so we get 1 over square root cos square u, and then instead of dy I write this expression 2 cos u over 1 square root 1 plus cos square u, and then you see here this cos square and root mean cos u, and this cos u is cancelled. We get this expression, and then in order to convert this expression into elliptic integral, I convert cos square u into sine square u. So cos square u is equal to 1 minus sine square u, and 1 and 1 is 2. So 2 minus sine square u we have get. But in elliptic integral we always have here is 1. So in order to make this 2 is 1, we take 2 as a common, and 2 is come as a square root of 2 because we have square root of 2 here. So I take common square root of 2 here, we get this expression, and when 2 is divided by square root of 2, we get square root of 2. And what is this? This is complete elliptic integral of first kind. Why first kind? Because this expression is in denominator, and what is k? K is square root half. You see here I write k is square root half, and what is angle? Pi by 2. Pi by 2 means this elliptic integral is complete, and elliptic integral is complete whenever first kind complete, we can write it as kappa of k, and k is square root half. So our this given integral is equal to square root to kappa of half, but kappa of k series is equal to this series from this expression, and our k in that example is square root of half. So I put k is equal to, in all these series is half, so we get this expression. Square root 2 I write as it is here, and in above expression I write pi by 2 as it is, then 1 plus 1 half square as it is, and then instead of k I write square root half. So I write square root of half square, and then square root half power 4, half square root half power 6, and so on. And then all these 4 terms we can calculate from calculator. We get our final result 2.66. So you see the given integral, we first convert into this complete elliptic integral of first kind, and then using the binomial expression of complete elliptic integral of first kind, we write into up to 3 decimal places. This is next example, and we have to again this integral we have to convert into elliptic integral. Remember, there is no short and fast rule for converting a given integral into elliptic integral, but when you solve many problems, you get some formulas or some tips in order to convert given integral into elliptic integral. So how we convert this elliptic integral into elliptic integral? You see here this is only cosine x, and remember in last time when you have only cosine x, whether it is in numerator or denominator, we bring this transformation, cos square u transformation. So similarly here we have cos x, so we also bring here is cos square u transformation. So see here, I assume cos x is equal to cos square u, and this transformation is actually the same transformation as this transformation I explain you here. So no need to again explain this same transformation here. I use, because this is cos x, so I use here cos square u transformation. We get dx is equal to the same transformation, and these are the same limit that we have discussed above. We get this expression, and finally we put this transformation into the given integral. We get this expression. Limit is the same, 0 to pi by 2, 0 to pi by 2, but instead of cos x I write cos square u. You see here cos square u, and instead of dx, you see dx, I write this value of dx. So I write here dx, and then this is the root and square cancel, cos u and cos u became cos square u, and I write this expression. And then I write this integral in, then I write this numerator cos square u into this form, 1 plus cos square u minus 1, and then I break this numerator into two parts. First part is 1 plus cos square u, and second one is 1. So when you break the first part, 1 plus cos square u, and in denominator root 1 plus cos square u, so half and 1 power should be subtract, and we get square root 1 plus cos square u du. And in second part we get minus 2 is because common, we get 1 over 1 plus cos square u. And now we want this integral should be in elliptic integral, so our aim is to convert cosine into sine integral. So instead of cos square I write 1 minus sine square, and 1 is 2, so we get 2 minus sine square. Similarly here we get 2 minus sine square u. And now what is the problem to become this integral into elliptic integral? We required here 1, so I consider 2 common here. We get square root 2 here, and here we get 1 minus half sine square u. Similarly here also we consider 2 common here, and that is square root 2 and 2 is cancelled, we get square root 2 here, and here we get 1 minus half sine square u. And now what is this? This is complete elliptic integral of second kind. Why complete? Because this expression is in numerator, and so this is second kind. And why complete? This is pi by 2, and complete elliptic integral of second kind is denoted by e of k. And what is k? K is square root half. Similarly, what is this? This is complete elliptic integral of first kind, because this expression is in denominator and angle is pi by 2, and complete elliptic integral of first kind is denoted by kappa of k, and k is again is half. So we prove that this given integral is equal to the subtraction of two elliptic integral. Now next example, we have to evaluate this integral, and actually evaluating this integral means we have to write these expression into elliptic integral form. So first I write the given integral as it is, and then I write sine square into 1 minus cos square. You may say that why I convert sine into cosine, because in elliptic integral we need here minus sign, and we cannot write here 1 minus 4 sine square for minus plus. But remember, in that case our k is outside, because k became negative. If I write here positive sign as minus of minus 4 sine square, then k our is minus 4, and k must be range between 0 to 1. So k is outside the range, so it will never become elliptic integral. So first there that's why I first convert sine x into cosine x, 1 minus cos square, so we get this expression, and then we can write this expression into this form. So our minus sign problem is clear, but we get here cos square, and in elliptic integral we need here sine square. So in order to make this cosine into sine x, we Example number 2, we told you that whenever we have to convert sine x into cosine x or cosine x into sine x, we bring this transformation pi by 2 minus y. So this transformation convert cosine x into sine x. So let's suppose x is equal to pi by 2 minus y implies dx is equal to minus dy. And when x is equal to 0, y is equal to pi by 2, and x is equal to pi by 2, y is equal to 0. And remember, cos pi by 2 minus y is equal to sine y. Now put these transformation into the last expression. We get pi by 2, 0, 5 minus 4, and here we write cos square, and instead of x we write pi by 2 minus y, but cos pi by 2 minus y is equal to sine y, so I directly write here sine y, and instead of dx I write minus dy. You see here minus dy, and because then I interchange the lower and upper limit, there is a minus sign, and that minus sign and this minus sign became positive sign, so we get this expression. And in order to convert this integral into elliptic integral, we need here 1. So for making 1, I consider 5 as a common. So use here square root 5, and here we get 1, and here we get 4 over 5 sine square y and dy. And what is this? This is elliptic integral of second kind, and this is complete. Why? Because the angle is pi by 2. And what is k? K is square root 4 over 5. So we can write this elliptic integral into square root 5 e of k, and k is square root 4 over 5. So our given integral, this integral is equal to this elliptic integral. Next, our aim is to express this integral in terms of elliptic integral, and remember x is between 0 to 6. So in order to write this given integral into elliptic integral, you may say, why we can not directly write it is into elliptic integral of second kind. So if I ask you, we can write it into elliptic integral of second kind, then what is k? You say k is 2, but remember, k is equal to 2 mean you are outside the range of k, because k is always in elliptic integral between 0 to 1, and you see here k is equal to 2. So you see this integral is like a elliptic integral of second kind, but it is not elliptic integral of second kind because k is equal to 2 here. So if k must be 0 to 1, then this will be elliptic integral of second kind, otherwise it will not. So our aim is to make this k is equal to 2 between 0 to 1, so that it became elliptic integral of second kind. So in order to make k is equal to between 0 to 1, we bring this transformation. You see here, this is actually square of 2 sine u. So we bring this transformation. 2 sine u is equal to sine phi, because you imagine instead of 4 sine square u, using this transformation we can put here sine square phi. So when you get sine square phi means the value of k is between 0 to 1. So we bring this transformation. 2 sine u is equal to sine phi, and from this transformation we get 2 cos u du is equal to cos phi d phi, and from this expression we get du is equal to this expression, and cos u can be written as square root cos square u, and then I write cos square u into 1 minus sine square u, and then I put sine square u. What is sine u? Sine u from this expression you see 1 by 2 sine phi. So I put sine u 1 because we have sine square u, so we get 1 by 4 sine square phi d phi. Similarly, for limit 0 to x, we have when I put u is equal to 0, we get 0 is equal to phi, and this means phi is equal to 0. And similarly, when u is equal to x, I put x is equal to, here we get 2 sine x is equal to sine phi, and phi is equal to sine inverse 2 sine x. So this is lower limit and this is upper limit. Now putting these transformation into this integral, we get this expression. You see here our limit 0 to pi, and here we get 1 minus sine square phi, and instead of du I put this expression. I put this expression, so we get this expression, and 1 minus sine square is cos square phi, and cos square and root is cancelled, we get cos phi, and this cos phi is cos square phi. So this expression we get this expression, and then I write this cos square phi into 1 minus sine square phi, and then I break this this numerator into this expression. Remember, we can write 1 minus sine square into this form, minus 3 plus 4, 1 minus 1 by 4 sine square phi. Why? Because 4 and minus 3 is 1. You see here 1, and this 4 is cancelled. We get minus sine square phi. So this expression and this expression are equivalent. But why we write this 1 minus sine square phi into this expression? In order to write our given integral into elliptic form. And then I break this numerator into two parts. First part is minus 3 over this expression, and second part is 4 over this expression. So from first part we get minus 3 by 2, 0 to pi, and d phi 1 minus 1 by 4 sine square phi. And from second expression, this 4 and 2 is cancelled. We get 2 here, and here we get 0 to phi. And here you see this power is square half, and here you see this power is 1. So 1 minus half, we get this expression. So what is this? This is elliptic integral of first kind. And because this is incomplete elliptic integral of first kind, so we write is f of k phi. And what is k? K is half. I write 5, and upper angle is phi, so I write phi. And similarly, what is this? This is incomplete elliptic integral of second kind. Why second kind? Because this expression is in denominator, and this is incomplete because angle is phi. So we write e of k. K is again half, and phi. And what is phi? Phi is sine inverse 2 sine x. From this, you see, phi is equal to sine inverse 2x. So we get our given integral into this expression. Jazakallahu khairan.